I'm going to record or set the recording to go. But I'll walk you through how to do it by hand one more time, and then how to plug this all the way in the calculator so that you can get a nice, good-looking digital answer. Because if you think about a problem that asks you to find limits as it applies to piecewise functions, and it's understandable if you don't know what a limit is yet. That's one of the reasons why you're here. But it involves you making the graph and then using it for other reasons. Then you're going to want to get technology involved quickly, because you don't want to get bogged down with the act of physically making graphs. All right. So, but just one more look at how you do it, or just I'll look at how you do it by hand. If you have two pieces, y equals 4 minus x. So that's using the domain where x is less than or equal to 2. I tend to look at that as negative infinity to 2. So where you're going from negative infinity to 2, bracket on the 2, parentheses on the negative infinity. Right. The other piece is x plus 2. But this time, where the graph begins at 2 and goes on to infinity, the difference here is you can't include the 2, right? Because it's got to be greater than 2. So we use parentheses to indicate that, right? So if you're doing this by hand, one way to do it is, I don't know what other people call it. I call it truncating the graph. So it's basically draw the whole graph and then chop off the parts you don't need. Right? So if I'm looking at y equals 4 minus x, it's a linear function. You know, if I were given a crazy transcendental function, you know, like a log or exponential or maybe some trig function, I'd probably go right to technology, you know, just to make my life easier. But a linear function, you might be tempted to just, I'll just crank it out by hand real quick. All right. So 4 minus x has a y-intercept of 4 and a slope of negative 1. All right, I'm going to draw the whole line. Like I said, I'm going to use a truncating approach. I'm going to draw the whole line. You don't need to plot all these points. I just need the points because of my inability to draw a straight line, even with the line draw tool. All right. Now, what this is saying is chop it off at 2. I only want to go as high as the value 2. All right. So if I'm looking along the x-axis, you know, I got my 1, my 2, my 3, and so on. For this is saying forget about anything after the 2. So I'd make a nice solid point at 2 and then just erase everything else. Right. In most cases, you won't even need to erase it. You'll just say, well, I'm just not going to draw any more of the graph after this because it's irrelevant. All right. For the second piece, we would start off, we have a y-intercept of 2 and a slope of 1. So it looks something like this if you were going to graph it in its entirety. But this time, I'm starting off at a 2, but I got to be careful. I'm not including the 2, so I need an open circle.
Isn't the y-intercept at positive 2?
Oh, positive 2. Thank you. All right. So I'm about to show you one of the benefits of having digital ink abilities. Yeah, I'll even slide it down a little bit.
Fancy.
Yeah, it's pretty not bad. Like, oh, I totally screwed up. Oh, wait, no, I didn't. There's no evidence that I messed this up. So very good. Thank you for pointing that out. I appreciate it. You'll find that sometimes I'm, you know, I like to think that I'm smart enough to walk and chew gum at the same time, but every now and then I start talking and I forget what I'm writing and vice versa. So anytime you catch me in a mistake, let me know. And then also, I know this is weird because it requires you to document the evidence of it. But if you catch a mistake in class, that I consider that a typo. You know, like you saved me from myself. Anything that helps me improve is always going to be a good thing. So then what you can do is you send me an email saying, there's no other way to say it except to say it. I was the one who pointed out the mistake in class today. And then I'll give you the bonus point towards your typo bonus, the 3 bonus points, right? So that's not open to anyone. That's open to the person who points out the mistake, obviously, right? Now this one starts at a 2 and goes on to infinity. So I don't need any of this graph here. And also I have to start it with an open circle, right? So I'm just gonna pop an open circle at 2. Best I can anyway. My drawing ability is better with the app, but it's still not good, right? So then this is what we're looking at in terms of piecewise graph, right? So it's not terrible when you have to, if you have to do it by hand, when it's a simple type of function, especially if it's like, something really simple, like just a point or a horizontal vertical line, that kind of thing. Well, vertical line wouldn't apply because it wouldn't be a function, but something simple like a horizontal line, pretty easy to do by hand. And sometimes it's worth your time to just do a quick, just scratch it out on a napkin and solve the problem that way. But let me just go over how to do this on the calculator, right? So we want to do some function, and we talked about this, I believe, last time, but I said I would go over it again because it's weird. And also, now that I think about it, I said that I would post up the Desmos in the online calculators link, and I forgot to do that. So that's another thing I got to add to my list. But first things first, f of x equals, we have 4 minus x. All right, but I only want this to exist in the particular domain x is less than or equal to 2. So I would open a squiggly bracket. So I go into the keyboard, and notation-wise, it's going to feel wrong because you look at this and you say, well, what does that squiggly bracket apply to? Just the x, the whole thing? Desmos understands that once you open a squiggly bracket, what you're about to write in applies to everything that precedes it. All right, so x less than or equal to 2, and then it truncates the graph for you, and now you have the first piece. Okay. The second piece, g of x, is equal to x plus 2. Open that squiggly jammy there, and then type in the x. You can use the x in either screen, greater than 2. And now we have that other piece, but the problem is it doesn't give us the open and closed circles, right? At least not as a static image. If you drag along, it'll plot a point there. If you drag along on the other one, it'll give you the open circle, but it won't leave it there by default, right? So a little nifty trick. Let's say, for example, you're doing a problem on the test and you have to create a piecewise graph, right, in order to find limits or do something else with it. Right? One thing that you could do, it's a little bit of a hack, but it gets the job done. Plot a point at each one of those endpoints. And you could get those points just by looking at Desmos, zoom in if you're not sure, in this case, 2, 4. So I'd plot 2, 4, 2, 4. It'll plot it as a solid point. And you're like, well, that defeats the purpose. But what you can do is long press on that icon there and change the type of point to an open circle. And now you have an open circle. All right. The endpoint, the one that I made for the black line, that closed circle, you don't have to really plot that. I only just put that there to accentuate the difference between the open and the closed circle. It's assumed that if you are not ending at an arrow or a closed circle, then, I'm sorry, an arrow or an open circle, that it's automatically default a closed circle, right? The one thing Desmos won't do, one of the things it won't do is put arrows on the end of your graph, but I'm not losing any sleep over that anyway. In fact, I have a Desmo somewhere where I actually built little arrowheads from little tiny line segments to put on the end of my graph. It was not worth the effort, right? So yeah, if you're taking a test and you want to submit this as your work, you're welcome to do that. All right. So you would save it. Let's say it's question 1 on test 1. You'd say test 1, question 1. That's the title. Throw your last name in there. That's always a good idea. And then once you do that, create a share link and submit your share link as your solution in Blackboard. All right. So that's something that's probably pretty different from what you've experienced in other math classes. All right. So that's a quick summary, a quick review. Right? And I'm just thinking, yeah, that Desmos that I created last time, I actually, now that I think about it, I kind of want to tweak it and make it a little bit better before I post it, but I will post it. All right. The next one, number 2, you have an absolute value function. You can graph that a couple of different ways. One would be by hand, right? Just like the other one, I'm going to take you through the by hand approach first, and then we'll get into the technological approach. For this one, I'll show you a TI method for it as well, right? So this is the standard form for an absolute value function. Absolute value functions are V-shaped graphs. So from this, we identify the A value, which is the slope, as -3, or quality equals, -3. The H and K, since the negative is already built into the equation, it becomes irrelevant. So H must be equal to 1. And the K value, because they're both positive, the positive signs become irrelevant. Oh, that zoomed out on me for some reason. Those are irrelevant, and so we would say that the K value is equal to 2. All right, so what we're looking at here is an absolute value function whose vertex is 1, 2, with a slope of -3. Now that negative just gives us direction. That means that it opens down. All right, so I would plot a 1, 2, and then counting off the slope of 3, so down 3, right 1, down 3, left 1, whatever, a slope of 3, but in the downward direction, I create a V shape with the point of the V being that vertex. All right, so we'd be looking at something like this. And so that would be our graph. All right. Now, if you're doing it on Desmos, not bad. I use F and G, so I'll use H of X is equal to -3. Put your absolute value symbol just by selecting that A with the absolute value bars around it, X minus 1. And one of the things I really like about Desmos, one of the many things, is kind of just what you saw there. And that is, as I started typing more information in, it started adjusting the graph. It actually does a good job of showing you what a transformation looks like when you adjust the H and K values, how the H is a horizontal shift and the K is a vertical shift. But from this, if I need to, I can get my vertex. I can get some points along the way. I got some y-intercepts here, x-intercepts. I got some arbitrary points along the way. I want to get some decimals involved, so a whole lot of possibilities. All right, but it's pretty user-friendly. User-friendly. I don't know why I was questioning myself on that, but it's pretty not bad when it comes to doing stuff like this. Now, let me show you the TI, because again, I don't know where you're going to end up after this course. You know, I don't know if your teacher next semester is going to be like, calculator, who said you could use a calculator? I've had tutors question my instructional strategies by saying things like, how do you learn math without by using a calculator? I'm like, you learn it pretty dang well, I can tell you that. You just don't get bogged down with the unnecessary stuff. Right? I got other teachers, they all say the same thing. I'm like, oh, why do you do it that way? It's like, because it works and it's good. Right? It's a good way to learn. You know, you just don't want to get caught up with, like, as a teacher anyway, you're teaching one way just because that's the way you've always done it. You know, that doesn't serve anybody in any way. So,
Professor, quick question.
sure.
So because the slope is negative, that means the absolute value graph opens down, right? That's why it opens down.
Exactamundo.
Okay, cool.
You got it. So for the TI calculator, for those of you who have one of these, and you know, even if you don't have one, if you like what you see, maybe you end up getting one. I'm singing all the praises of the Desmos calculator, but that's because I'm very well versed in both of them. And so, you know, like, if you're just starting out, you're kind of an open, I don't want to say open book, that doesn't make sense, but like, you're open to different possibilities, right? So hopefully, anyway. So you'd hit y equals, and we'd clear out all this stuff. You would type in -3, then you need the absolute value symbol. There's two ways to get it on a TI. You could hit alpha window, and the very first option you see there is an absolute value function. Or you can go into the math menu, and you see all these different options. When you go column to column, in the NUM menu, so math followed by NUM, you select absolute value or ABS. With the newer TI 84s, or even the older ones, but with the operating system, it should bring up an absolute value set of brackets, right? The vertical brackets. So then you just type in x minus 1, hit the right arrow to get out of the absolute, and then +2. Right? And then you can just do a quick zoom 6. That's the standard zoom on the TI calculator. So zoom 6, and that'll bring you to the graph. And I'll just pinch zoom mine, because mine's an emulator, so it's not quite the same, but it's the same enough, I guess, if that's even remotely good grammar. And so you end up with this graph. If you hit second graph, it brings you to a table of values, which is what you see here. And then you could plot the points, just like with a parabola. If you have a table of values, you're looking for symmetry in the y column. Once you find that symmetry, you know that the point that it's symmetric about is going to be your vertex, so 1, 2, and the other points will just help you, create the rest of the graph, right? So just a little look at the TI calculator, just to remind us that that's a thing. Okay. So I'll do another one, because they don't, I don't want to bore you to death here, but I also want to make sure I get the point across. Number 6 is a good one. Let's tackle that one real quick. The answer key for this entire packet is, oh, you know what? Actually, I was going to say it's on my website. It is on my website. I just haven't linked my website to Blackboard, so I'll make sure to do that later also. Let me just add these things to my list of things to do before I forget. So I want to link the piecewise calculator, and I want to link the answer key for the packet. Okay, So I'll remember to do that now. So let's take a look at numbers. Yeah, go ahead.
When I put the function, the absolute value function in my TI, I got that the x-intercept was 0. Value was 0 and the y value was like 1.4 or something.
Huh. So the x-intercept was 0.
The x value was 0, and then the one for the vertex, I mean.
Oh, okay.
And then the y value was like 1.4.
So you typed in -3 absolute x minus 1, then you closed up the absolute, then the +2?
Yeah.
Huh. Just trying to think how that could happen. All right, let me just check something real quick.
It might, my calculator was like loading for a long time and I kind of just shut it off. So it might have just been like bugging. I don't know.
It could be.
Let me try to enter it.
Okay. If not, send me a picture of it, of what you have in your calculator, and I'll see if I can diagnose what the problem is. I'm just curious about. No, that's not. Sometimes, you know, if you get the absolute on the wrong side of the.
Oh, no, it regraphed perfectly.
Oh, worked this time? All right.
Sorry.
No, it's all good. Rather figure this stuff out now than have you wondering what went wrong, you know. Well, let's take a look at number 6 on the next page. Again, we have 3 pieces, and just like I did before, I'll do it by hand, but I'll do it a little bit quicker this time. By hand, and then using Desmos. So we have -x minus 1, but only for values of x that are less than 0. So that's -infinity to 0. So y-intercept -1, slope -1, so down 1, right 1, down 1, right 1, and then going back the other way. And then before I even draw the line, you know, I'm going crazy plotting points here just out of habit, but before I draw any line, I'm going to say, okay, well, which part of this will not make sense? So I want to cap this off at 0. 0 for x is right here. Because again, when we talk about domains, we're talking about the x-axis. So 0, 1, 2, 3, and so on, and also going in the negative direction. All right. So at 0, we would stop the show. All right. So I can get rid of everything that comes after 0, but also add 0 because of the parentheses. This has got to be an open circle. All right, so I'm going to replace this with an open circle. So now I have that piece. The second piece is kind of weird. All right, that one says y is equal to 5 when x is equal to 0. All right, so the domain is just the number 0. So this would normally be the line y equals 5, 1, 2, 3, 4, 5, horizontal line. It would look like this. 1, 2, 3, 4, 5, bring it down 1. But it's saying I only want it when x is equal to 0. Well, that's right here and nowhere else. So then I would say, okay, well, I don't need anything that's bigger than 0, and I don't need anything that's smaller than 0. So I'm really just looking at a single point. All right. So in a piecewise function, if you just see a constant value followed by a specific x value, not an interval involving x, then you're talking about just a coordinate. All right? People get jammed up on that all the time just because it's just so weird looking. And it also kind of gets you down the road of thinking, well, if it's a coordinate, why not just write it that it's a coordinate? I mean, this is a notation that's a catch-all. It works for all possible situations involving functions. All right. The last piece is x plus 2. So we'll do that in green. Y equals x plus 2. But starting off at 0, going to infinity. All right. So x plus 2. All these points here, but only going to infinity. So I don't need all these points here that I'm drawing in. I don't need any of these, because I want to start at 0. However, because it's parentheses greater than, we're looking at an open circle. So at 0, I'm going to replace that with an open circle and draw a nice line segment with an arrow at the end, array if you're being technical. And so that would be my piecewise graph. All right, each one of these 3 pieces. So this one, and this one. Now, in Desmos, you want to, like I was saying before, when you do your work in Desmos and you realize, that was pretty complicated, I'd like to save that, then by all means, save it and use it again. So what I'm going to do is I'm just going to build off of this. I have a negative x minus 1. X is less than 0. All right, so that's one piece. All right, the color scheme is a little out of whack. It's not going to be consistent, but that's okay. The second piece is just a 5. Now, I kind of look at that and say, well, I don't want to waste all the good work that I did in my G function here. So what I'll do is I'll tap or click on this little gear icon, and you see the option, the 2 little sheets of paper there with the folded tabs. That means duplicate. So, and I'll show you what that little table thing means in a minute. But you duplicate it, and then what I can do after I hit done, now I have 2 G functions. There's a little bit of a conflict there, but I can actually get rid of this one and call my second G, just go back and call that H. So now I can kind of make use of the fact that I already typed some of this stuff, because I already typed an x plus 2. I don't want to get rid of it. So I would make my H x having x greater than 0, and then go back to my G and make that a 5, but only when x is equal to 0. Okay. So like nothing showing up on your screen. That's because I turned off these functions. So I'll just tap them on. Now the thing about this one, the G where G of x is equal to 5 if x is equal to 0. That there's kind of like a little bit of a philosophical issue there, right? Because what Desmos assumes, and it's actually correct, when you're dealing with a function, it's saying that I'm looking at a horizontal line that only exists at a one-dimensional point. One-dimensional points don't show up the same way on a 2-dimensional plane as a one-dimensional point would show up on a one-dimensional point. All right, so bottom line is there's a 0, 5 there. It just doesn't show up. I mean, you could try to zoom in all you want, but it's like looking at the head of a needle if the needle was infinitesimal in terms of its width. Right, so it's just not going to appear. Right, so there's a couple of ways to handle that. One would be to kind of break the rules of math here and try to make the thickness something more substantial, but even still, that might not work, right? Because Desmos doesn't think the right way, right? The other way is to kind of call it a day and say, all right, well, I'll just plot a point there, right? So you kind of decide on the fly what makes the most sense. In most cases, you're going to want to plot a point, right? So 0, undefined, that green line, the one on the left that's red on when I hand drew it, that should be an open circle. This point should also be an open circle. So I'm going to plot those. So it's 0, 2. So I got a point there. And I could duplicate. The benefit of duplicating as opposed to doing it from scratch is if I plot a point, you're like, oh, I could just type in, what is this one? 0, -1, 0, -2. I could just type it in. But if I use duplicate, actually it is 0, -1. So let me fix that. I counted 2 boxes and I just didn't consider the scale. if I hit duplicate, it'll save the settings from whatever I'm duplicating. So I had it set to open circle, so it'll keep it as an open circle, right? And then when I want to plot the 0, 5, I could just do that as I normally would, 0, 5, right? And so now you have a point there. You know, sometimes it doesn't pop the way you want it to. You kind of look at it and say, well, is he going to know that there's a point there at 0, 5? I mean, yeah, probably. But if you're not sure, then change the color scheme so that it stands out a little bit more. So maybe you go with red. So long press on the icon and just change the color to red and make it red across the board. You know, sometimes the graph's still a little too noisy. So if you go into this little wrench here, you could tap on grid to get rid of some of the extra stuff. And it kind of pops out a little bit more. Right. So I'm thinking, like, on a test, you want to submit a nice high quality piece of work. This would be the work that you would submit. Right. Now you got all this stuff on the side here, but you wouldn't necessarily be doing that from scratch because, you know, what is this? This is page 5, number 6. So if it'll let me. I don't know, I had to tap on the icon like 50 times in order to make it work. But so I'd say Calc 1 notes, page 5, number 6. Right. And so now when you go through your little log here, your little history, and you're saying, oh, this question on the test, that really reminds me of that problem we did in class. You open your notes, you see, oh, that's page 5, number 6. Go into your Desmos, look for your Calc 1 notes, page 5, number 6, open that up and say, okay, well, at least I'm a step ahead here. All right. So this is it's an avenue for you to not only become familiar with the technology, but also so that you can be more efficient in your problem solving. All right. And if at any point you have questions about Desmos, let me know. The one time, unfortunately, you really can't ask me any questions about Desmos would be during a test, right? Because if you're choosing to use a technological approach, you're on the hook for knowing the technology. But anytime before the test, you can certainly ask, right? So just make sure that you're taking the time to do this because, you know, I have stories from previous semesters galore, but one that pops out in this particular moment is it was actually last year. I think it was Calc 3 class. It was fall semester. I remember it like it was. No, a student in the middle of a test was like, so how do you do that stuff on Desmos? And I'm like, what stuff are we talking about? He's like, and then he named something. I'm like, that's like the whole point of the question. So if you don't know that, then you're already behind the 8 ball. Right? So take the time. Right? It's definitely user friendly. Also, I mean, I'm doing this on an iPad, but Desmos works pretty well on a phone. Also, you don't even need the app. Just go to desmos.com and then click on the graphing calculator and it'll open right up. All right. So even when you're just hanging around and you're like, all right, he said to look at this Desmos stuff. Let me take a minute and look at it. You'll find that there's a lot more to it than you might realize in terms of its use. All right.
Hey, Professor.
So, yeah.
So when we have a test, are we gonna have to show you the work through Desmos, or like if you do it on paper, how would you do it?
If you're doing it on paper, then you'd submit your paperwork. So you would take a picture of your work and submit that as a file upload on Blackboard.
Okay, all right, that's fine.
Okay. So you have the opportunity to do it either way. Just giving you options.
Okay.
Options are good. All right. So on page 6, and like I said, I'll make the whole answer key available later. So you'll have answers to all these problems too. On page 6, we talk about continuity, increasing, decreasing, and constant functions. But in order to really talk about continuity, we're going to talk about discontinuities. All right. So a continuous graph is any graph that does not contain a discontinuity. All right, so that's kind of a cop out in terms of a definition, right? Because you kind of look at it and say, well, isn't that sort of the same as using a word in its own definition? And my answer is, yeah, it sure is. But this is one of those paradoxical situations. In order to understand limits, we have to have a working definition of continuous graphs or continuity. But in order to truly understand continuity, we need to know limits. All right, so this is we'll call it a placeholder definition until we really truly get in depth on the concept of continuity next class. All right, so discontinuities, I'm just going to use my highlighter here to emphasize them. They're really any kind of break in the graph. So you could have a point discontinuity, a jump discontinuity, or you could have an infinite discontinuity. All right, so that's a break in the graph. All right, an old school definition. In fact, it was the definition that I was given when I first learned about continuity. Same explanation too. It's like, well, we got to use some kind of definition until we can really talk about continuity. But it was if you could draw the entire graph from beginning to end without picking your pencil up off the paper. So that was a decent working definition. But invariably you have the contrarians in the group that say, yeah, I can draw a graph from beginning to end without picking my pencil up off the paper. Here's an example. And you're like, oh yes, mission accomplished. I drew the graph without picking my pencil up off the paper. The problem is there's a discontinuity here. It's a point discontinuity. All right. When you have a hole in a graph, that's what a point discontinuity is, a hole in the graph. We don't actually have a graph that contains an open circle like you see on the Desmos here. We just use the open circle to represent really the event horizon of the hole. Right? And there's a reason why I use that term, because it really is like a singularity, like a black hole, where you have that infinitesimally sized singularity, that gravity well, but it's represented by the event horizon, and that itself is not the black hole. That's the stuff that's being pulled towards the black hole, including light. Right? So it's the gravitational pull that's caused by the black hole that creates the appearance of the event horizon and also the physical manifestation of the event horizon. But the black hole itself is that you can't even quantify it. Right? It's a one-dimensional break in the fabric of space. Right, so that's what we're looking at here, and that's also why calculators like the TI calculator, and I think if I'm not mistaken here, let me just open up another Desmos. If I graph this one, for example, f of x, it'll graph it and it'll plot in some capacity a hole. It's just, it doesn't accentuate. We accentuate the hole by using an open circle, just to make it appear obvious. But you look at this and you say, okay, this is just a good old fashioned parabola, right? But there is a hole in this graph at x equals 2. All right, and I'll walk you through that in a minute. But if I go to x equals 2, I don't see a break in the graph. All right, if I zoom in, Eventually, I get to a zoom factor where the calculator's like, yeah, there's no point here, but I don't really know how to represent a one-dimensional feature on a two-dimensional graph. All right. But it's one hell of a zoom factor in order to get in there. All right. So what we do is we either do the drag along the, I'll just hit the home key there, drag along the graph, and hope that we stumble on the point that doesn't exist. And if we do, I'm going to the wrong thing. Where am I? I got to go higher. I was looking at the wrong thing. Yeah, eventually you stumble on it, and it'll give you that open circle to indicate that there's a hole here. Okay. Or you plot the hole yourself. The key is understanding when there is a hole in the graph. Right, because sometimes you get it's of course a habit. You know, you start typing functions into a calculator, and you're like, okay, I guess it's a parabola. You don't even look at what kind of function it is, and then all hell breaks loose. Right. So what we would have to do is simplify the expression any common factor could represent a hole or a point discontinuity. All right. So it has to be an instance where the function would be undefined. But then when you factor out that common factor, it's no longer undefined. The location of that common factor on the graph would be the location of the point discontinuity. We also call these removable discontinuities because you can create a graph that looks the same without having that discontinuity. All right. So what I would do here, you could do it a couple of ways, but I would factor. And in this case, I would only be factoring because it is factorable, right? So if you don't remember, I'll just kind of jot the rule down on the side for a difference of two cubes. The rule is if you have an expression in the form of a cubed minus b cubed, it's going to factor to a minus b times a squared plus ab plus b squared. All right. That's something from early college algebra, but doesn't always come up, you know, so it's easy to forget. All right, but if I follow that model, I'd be looking at x minus 2 times x squared plus 2x plus 4. All right. Really, it's just a matter of identifying the a and b values. Once you do that, everything else kind of falls into place. All right. So if we kind of match it up, you would say, well, if this is, you know, a cubed minus b cubed corresponds with x cubed minus 8, then we would be saying that a is x and b is 2. And then you just run through your model by saying, all right, well, this would be an x, this would be a 2, this would be an x squared, this would be a 2 times an x or an x times a 2, and then this would be 2 squared, which would be a 4. All right, so that's a quick refresher, but you know, it doesn't always come up, so you don't always have to really worry about it. Right. Another way to do it, to simplify a rational expression, especially when the numerator has a higher power than the denominator, would be using division, whether it's synthetic division or long division. You can simplify that way. I'm going to go over synthetic division in a little, well, not today, but you know, not too far into the future. So so you'll get a review on that. But if you have some time on your hands and you want to refresh your memory on synthetic division and long division, that's probably not the worst idea in the world. Right? So, but yeah, this would be the quickest of reviews on how to factor difference of two cubes, right? Regardless, one way or another, it should simplify down because we have a common factor of x minus 2. So this would simplify down to x squared plus 2x plus 4. All right, that common factor will no longer be relevant in my simplified function. All right, so this original function is undefined when x is equal to 0. I'm sorry, x is equal to 2, when the denominator is equal to 0. All right. If x is equal to 2, it would be undefined because it would make the bottom of the fraction equal to 0. But once you remove it, it's irrelevant. So it's irrelevant for this new function, but it's always going to be irrelevant for the original function. It's an excluded value, right? So if I were to type in just a simple y equals x squared plus 2x plus 4, you see that I'm looking at the same graph, right? Parabola, parabola. It's the same graph, except this one, when I get to the x value of 2, it actually gives me a y value. The other one said undefined, right? So this one wouldn't have the hole, if I can get it to stay on there. This one wouldn't have the hole, but this one would. Now you could still ballpark it and say, okay, it says 2 comma undefined, but as I get closer to 2, it seems like it's getting closer to 12. It looks like it's at 12. If I go to the other side, it comes off of 12 and increases without restriction. So odds are it's 212, but you don't get the confirmation until you get right here. You know,
How is it possible if you simplify the same function that one has a hole and one doesn't?
Anytime a denominator disappears, one of them is going to have, so the original had an instance where it would be undefined, but this new function doesn't have a denominator, so there's no instance where it would be undefined. Right? So it's the same path, except they're not equivalent graphs. They just appear to be. You know, that's the thing that trips people up, because this graph is not the same as this one. It's mostly the same, but it has one key difference. All right, because we're able to remove that x minus 2, we have a simplified expression leading to almost the same graph, but with that one key difference being that one of them has a hole and the other doesn't. Right?
So wouldn't you have to call it like, you can't still call it f of x, you'd have to call it like h of x or different?
Yeah, you could call it something else. Yeah, in fact, we're just using this as kind of like sort of a placeholder is not the right word, but it's an avenue to get all the convenient points in the graph without having to work with this whole thing. It's sort of like saying, all right, if I know that the only two differences between these two graphs is one has a hole and the other doesn't, and I know the location of the hole, then I would, and I think most people would agree, I would graph the easier of the two functions, whichever one is easier to graph, and then just take note of that key difference and just pop it into the new graph. But yeah, they would be two separate functions, right? So when I plot this, I can do it just by grabbing some points off of the blue one, 1, -3. 212 is going to fall off the grid. So if I'm doing this by hand, I do need to scale this one. So 1, 2, 3, 4, 5. I'm going to go by threes. 3, 6, 9, 12. For the x-axis, I'll just go by ones. You can scale your horizontal and vertical axes different from one another. There's no, I mean, without any context, you know, without it being a word problem or anything like that, you don't have to worry about, you know, having square increments. So -1, 3. Then I got a y-intercept here at 0, 4. I'll just ballpark that. I know it's symmetric. So I'll ballpark that one. And I know 212 is going to give me an open circle. So I'll put an open circle here. That's the only open circle. So at, let's see, that would be 1, 2, 3 units away on the right. I go 1, 2, 3 units away on the left and I plot a point there just to give myself a little bit of symmetry. And I'd be looking at the best I can do in terms of creating a graph by hand. And so it's really not too bad. Now, let me just take a second and show you on the TI. It's really essentially the same process, but there's some slight differences. It's really just how you type things in, right? So on the TI, you could put a fractional expression in one of two ways. One way would be to use parentheses and division. Another way would be to hit alpha y equals, select n over d, and it'll bring up a fraction toolbar. So alpha y equals, and you'll see an option n over d, or numerator over denominator. And then you would just type in x cubed, so x caret 3, right arrow, get out of that exponent, -8, and then x minus 2. And then as a separate function, I would type in the simplified form, which is x squared plus 2x plus 4. I can look at the graph, again, zoom 6 to get a standard viewing window. But this one, the hole doesn't occur until you get to 12. So when you go to your window, you might want to do something like -10 to 10 for x, but then maybe 0 to 20 for y, and then create the graph off of that. All right. So then just hit graph right away, and you'll see when you go into the table, right? It's a second graph to bring you into the table. If you scroll down, you'll see an error message or undefined for one of the functions when x is 2, but you'll see an actual value for the other function when x is equal to 2, and that would be the indication of a hole. All right. So little weird, little tricky. Point discontinuities. Honestly, I mean, I'd be surprised if that was covered in the previous course. It's supposed to come up in pre-calc, but sometimes it gets skipped. Sometimes it's just glossed over. But yeah, that's the first probably tricky part of the review of previous courses that we've gotten into. Right. The jump discontinuity is actually really easy now that we've talked about piecewise functions. Right. Just a matter of graphing this. And I'll just scratch this one out by hand, because we're looking at y equals x minus 1, going from -infinity to 0, and then y equals x plus 3, going from 0 to +infinity. So x minus 1, y-intercept of -1, slope of 1. So we're looking at a graph like this. But then, like I've been saying, you just erase or disregard the parts that don't make sense. In this case, I want to max out at 0. So I get rid of anything north of 0, but also it's got to be an open circle. So open circle at 0. And despite the fact that these look like open circles, that's just my crappy ability at drawing. So I'm going to darken those in and draw a line segment, slap an arrow on the end of it, making an array. And now we have the first piece of the function. Right? The second piece of the function is going to have the same slope, but a y-intercept of 3. Now this one's going to start off at 0, at the x value of 0. So we don't need any of these points here. All this stuff, we don't need any of that, because it's starting off at 0 and increasing from there. All right. So there's definitely a break in this graph. If we're working from left to right, if we're reading the graph from left to right, we're following along this path. But once we get to this location, we have to then jump to get from one piece of the graph to the other piece of the graph. All right, so it's a clean break in the graph. So a jump discontinuity is talking about a vertical displacement between pieces of the graph. All right, so a vertical displacement between the pieces of the graph. Now, it's possible that there could be a vertical and also a horizontal displacement, but you don't get a jump without there first being a vertical displacement. All right, if there's also a horizontal displacement in there, great. It's the vertical that we care about. All right. So those are very easy to identify. The infinite discontinuities are also very easy to identify. Most commonly, they're vertical asymptotes. But you're talking about graph. Well, it's really pieces of the graph, but the graph approaches infinity in the y direction. So this graph has a vertical asymptote because we don't have a common factor that can be canceled out. Sorry, I'm just cleaning this up a little bit. Doesn't look much better, but I'm willing to live with it. This graph doesn't have a common factor. There's nothing that you can cancel top and bottom. So if we set the bottom equal to 0, we get a vertical asymptote. All right, so I'd subtract the 1 from both sides and we get x equals -1. All right, so I would plot that as a vertical line, but also dashed. Not good. So that's my vertical asymptote. My horizontal asymptote, not always relevant, but in this case it is because we have the power of the top being equal to the power of the bottom. So my horizontal asymptote is going to be the ratio of the leading coefficients, right? So the leading coefficient on the top is a 1. The leading coefficient on the bottom is a 1. So my horizontal asymptote is going to be 1/1, which is 1, which is telling me that I have a horizontal line that the graph is going to approach in some capacity. All right. So to create the rest of the graph, I mean, it's not an algebra class, not pre-calc. I mean, if you want to go to technology to do that, you can, but you can also grab an x-intercept, a y-intercept, and see what's going on there. Like if you want to get a y-intercept, it's very easy. You just replace all the x's with 0 and simplify. In which case you'll get a 0. So that's a nice point that we can plot. You can plot some other points too, but the idea here is if you really consider what's happening in this graph, by the equation, you have x divided by x plus 1. So you think about some examples of that. Like if x is equal to 1, then the value of the function would be 1/2, 1/1 plus 1. Right? If x is equal to 2, it would be 2/3. If x is equal to 3, it would be 3/4. If x is equal to 4, it'd be 4/5, then 5/6, then 6/7, then 7/8, then 8/9, and 9/10, and so on. You start thinking about what this possibly could be approaching as you increase the value of x. It's going to approach the number 1, right? Because if I have, let's say, 99 over 100 or 999 over 1,000, decimal wise, it's getting closer and closer to the value of 1. So the graph would have to look something like this. Right? But it also has to approach that vertical asymptote. So it would have to necessarily bend down and start trying to go vertical as it goes from right to left. Right? So that's a strategy that you could use. You know, you can kind of look at, see that vertical asymptote at -1. So let's say I put in a -2, I would get -2 over -2 plus 1. So -2 over -1, which is a +2. So that would plot me right here. And if I'm using the same ideas over here where I'm approaching both pieces, I'd be looking at something that looks like this. That's operating under the assumption that you're interested in doing this by hand. All right. Oh, you don't need to see my email. Jeez, I hit the wrong thing. There's nothing. Oh, I keep hitting the wrong thing. There's nothing suspicious or conspicuous in my email. Because it doesn't need to be open during a YouTube recorded lesson. That's as simple as that. Anyway, so yeah, Desmos is what I wanted to open. So f of x, if it'll let me, come on, there we are. F of x is equal to x over x minus x plus 1, sorry. And so now you have the graph. And that's what I drew, so we're in pretty good shape. But you can also see that as you work your way out to the right, it does appear to be getting closer and closer to a +1. All right. As you work your way out to the left, it does appear to be getting closer and closer to the +1, but on the high side. Right? It's decreasing to a +1. All right. But as you get closer and closer to the x value of 1, moving in from the left, if it'll let me, come on. See, it starts increasing without bound, this point. You know, it's going a little bananas on me, but you know, you get the idea. If not, you can just start zooming out big time and you see, oh yeah, it's definitely going up forever. Right. So that's a possibility. Another thing that you can do if you want to get really precise numerically with this would be to evaluate the function for some arbitrary value a. So type in f of a and create a slider. Right. And so this is kind of the building blocks of understanding limits. So if you get a handle on these types of discontinuities, your understanding of limits is going to come a long way. But let's say I wanted to see what was happening to the y values, because that's what f of anything tells us. It tells us the y value at a given value of x. But only as I get closer and closer to the x value of -1 coming in from the right. Sorry, my thing just crapped out. It crashes sometimes because I have like 15 different files open. But then it always comes back, so we're good. So what I can do here is, let's say I want to go from, instead of -10 to 10 on my slider scale, see it goes from -10 to a +10, doesn't really tell me much. Let's say I want to go from -2 to -1. All right. So I'd make my low bound here a -2, my high bound a -1. And then I would change my step to be smaller than 1. Right. So maybe like 0.01. So then when I do my sliding, it's going by hundredths of a unit. And you can see you're kind of numerically showing that increase as you get closer and closer to 1. And it actually gets very large very quick until it goes to undefined once it gets to -1. You can kind of see it in action. Now, something a little bit nicer would be if you actually wanted to have a point move on the graph. Right? The way you would do that would be to plot a point. A point would be normally x comma y, right? But if my x value is now represented by the letter A, I can type in an A here. If my y value is now represented by the f of A, I can type an f of A here. And now it'll plot a point on the graph, right? So what I can then do is I can manipulate my slider and that'll move the point for me. And you can see that point moving and you're like, oh, how's that different than just sliding it yourself? Well, now I can animate it and let it do its thing without me being necessarily involved in it. All right. So you kind of set it and forget it. So you have that going on there. And then if you want, you can have it coming in from the other side, approaching a -1, but from the right. So between -1 and 0. So I could change the bounds of my slider going from -1 to 0. And then run it there, you know, or you can go -2 to 0. You know, you can manipulate it any way you want, just so you can see that point in motion as you go. This is going to actually help us a great deal when it comes to understanding limits. All right, so this will be, I'm going to save this one for you also. All right, so, yeah. Next class, we're going to talk about oscillating functions, increasing, decreasing, constant, and continuity, and then we're going to get pretty heavily into limits. But what I wanted to do, it's 7:20, so what I wanted to do is give you the time to get started on your tech assignment. All right, so I'm going to stop the recording